everyone, today we're doing notes for 8.3, testing a proportion P. The null and alternative hypotheses for tests of proportions are, we have the left tail test, right tail test, and two tail tests that are similar for when we're testing for means. So we will always start with the null where its P is equal to some value K. And then left-tailed test, the alternate is P is less than K. For right-tailed test, P is greater than K. And for two-tailed test, P is not equal to K. Note that since P is a probability, the value K must be between 0 and 1. So to test a proportion, we're going to consider a binomial experiment with n trials where P represents the population probability of success and Q equals 1 minus P represents the population probability of failure. Let R be a random variable that represents the number of successes out of the n binomial trials. The number of trials n should be sufficiently large so that both n times p is greater than 5 and n times q, which is n times 1 minus p, is greater than 5. Remember, n times p, this represents your number of successes. And n times q, or n times 1 minus p, this represents the number of failures. Okay? The sample test statistic p hat is r divided by n, and this can be approximated by the normal distribution. So then here's our procedure. You'll see it's pretty much the same as for means. Our test statistic, z is equal to p hat minus p divided by the square root of p times 1 minus p divided by n. And then we will go through finding our test statistic, our p-value, and then making an appropriate conclusion. All right, so here's our first practice. It says, a team of eye surgeons has developed a new technique for a risky eye operation to restore the sight of people blinded from a certain disease. Under the old method, it is known that only 30% of the patients who undergo this operation recover their eyesight. Suppose that surgeons in various hospitals have performed a total of 225 operations using the new method and that 88 have been successful. Example, the patients fully recovered their sight. Can we justify the claim that the new method is better than the old one? Use a 1% level of significance. So let's label what we have here. We have that it is known that only 30% of the patients who undergo this operation recover their eyesight. That's important. We have these two values. We have a total of 225 and that 88 have been successful. So 88 is going to be our R and 225 is going to be our N. Okay? We want to check, can we justify that the claim that the new method is better than the old one? And we have a 1% level of significance. So for A, it says establish our null hypothesis, alternate hypothesis, and note the level of significance. I would like you to do this, please. Okay, for this one, our null hypothesis is going to be P is equal to 0.3. Our alternate hypothesis is going to be P is greater than 0.3 because we want to see if it's better. And then our level of significance, alpha, is going to be 0.01 because it says 1%. All right, to check our requirements, is the sample sufficiently large to justify the use of the normal distribution for p hat? Find the sample test statistic p hat and convert it to a z-value if appropriate. So we have to check our n times p. So this is 225 times 0.3, which gives us 67.5, which is greater than 5. Okay, then n times 1 minus p. So 225 times 0.7, which is going to give us 157.5, which is also greater than 5. So we're good there. So we can use the standard normal distribution. All right, so now p hat is going to be R divided by N. So 88 divided by 225. If we want, we can write this as a decimal, 0.3911. And so let's do our test statistics. We have z is equal to p hat minus p divided by square root of p times 1 minus p divided by n. So this is 0.3911 minus 0.3 divided by square root of 0.3 times 0.7 divided by 225. So when we calculate, this is going to give us 2.9819. Notice this is a right-tailed test, and we got a positive z value. All right, for C, I want you to find the p-value of the test statistic. Please do this. Okay, so to find our p-value, that's going to be the probability that our z is greater than 2.9819. So we're going to do normal CDF of 2.9819 up to 10,000, comma 0, comma 1. And this gives us 0.0014. Okay, so now we have to conclude the test. We compare our p-value to alpha. So our p-value is 0.0014. Our alpha is 0.01. In this case, p-value is less than or equal to alpha, so we reject the null hypothesis. Interpretation, interpret our results. We would say we have enough evidence to conclude the probability of success of the new method is higher than the old method. Okay, here's our next question. A botanist has produced a new variety of hybrid wheat that is better able to withstand drought than other varieties. The botanist knows that for the parent plants, the proportion of seeds germinating is 80%. The proportion of seeds germinating for the hybrid variety is unknown, but the botanist claims that it is 80%. To test his claim, 400 seeds from the hybrid plant are tested, and it is found that 312 germinate. Use a 5% level of significance to test the claim that the proportion germinating for the hybrid is 80%. Okay, so let's underline important things. So the botanist claims it's 80%. We have 400 seeds, so this is our N. 312 germinate, so this is our R. 5% level of significance. And we want to test that the proportion germinating for the hybrid is 80%. All right, so let P be the proportion of hybrid seeds that will germinate. Notice that we have no prior knowledge about the germination proportion for the hybrid plant. State our null and alternate hypothesis. What is the required level of significance? So our null hypothesis is going to be that our P is equal to 0.8. Because we have no prior knowledge and we want to just test if it's 80, our alternate hypothesis is going to be P does not equal 0.8. Our level of significance, alpha, is 0.05. All right, check our requirements. So we have our N times P. So this is going to be 400 times 0.8. That gives us 320, which is greater than 5. Then we have to check N times 1 minus P. 400 times 2, which is 80, which is also greater than 5. So yes, we can use the standard normal distribution. All right, calculate the sample test statistic p hat. P hat, remember, is r over n. So in this case, we have 312 divided by 400, which reduces to 0.78. All right, so we want to convert this to a z value. So I'm going to show you how to do this one in the calculator. So in your calculator, this time we're going to choose the 1 proportion z test. So if you recall, in order to find this, we're going to hit stat. Then we're going to arrow over to tests. And then the 1 proportion z test is choice 5. Okay, again, choice 5. So for this one, our P0 comes from our null hypothesis. So we're going to put in 0.8. Our X is going to be 312. Our N is going to be equal to 400. And we're going to choose that our proportion does not equal P0 based off of our alternate hypothesis. So go ahead and calculate this one. And we should get for D that our Z is equal to -1. All right, I would like you to go through and record the rest. I want you to say what your p-value is. Say if this is right-tailed, left-tailed, or two-tailed. And then say if you reject or fail to reject the null hypothesis, and interpret. Go ahead and do this. Okay, in this case, because we had not equal to, this is a two-tailed test. Our p-value, we can see from the calculator, is 0.3173. So we compare the p-value, 0.3173, to our alpha, which is 0.05. And in this case, p-value is greater than alpha. So we fail to reject our null hypothesis. So to interpret this, we would say we do not have enough evidence to conclude the germination rate is not 80%. This is just a reminder here of where the test is located again for you. We are not going to do 8.5. This is actually the end of our notes for the semester. So that's all I have for you.